Hello, I'm Michael O'Connell, and in today's video we're going to derive the Rachford-Rice equation so that we can perform flash calculations for a mixture at a given temperature and pressure. In the next video we'll be using the Rachford-Rice equation that we derive to do a very simple flash calculation. In a flash calculation, we have a container that has our mixture and a feed that deposits our mixture into this container, and we are given the temperature and pressure of that container. And at that temperature and pressure, our feed of the material will separate into vapor and liquid phases. And we're interested in calculating the composition of the vapor phase and the liquid phase and the amount of vapor phase and liquid phase that we have. So that is the purpose of the Rachford-Rice equation and what we are going to be using it for in the next video. Now we're ready to derive the Rachford-Rice equation. So I have a flash drum here on the whiteboard, and as you can see over here on the left, we would have some sort of feed going in, which can be at some temperature and pressure. It can be all liquid, all vapor, but this has our mixture inside it. And in this very simple situation that we are going to deal with, we are actually going to know the temperature and the pressure inside of our flash drum. Now, the only comment that I'm going to make in this video about this temperature and pressure is that it is very, very specific, and it relates to what we did in the last video with the dew pressure and bubble pressure curve in this case, right? So we have a constant temperature, and then on this axis we have the mole fraction of our more volatile component. So that could be, X1 or Y1, something like that, okay? We have our two-phase envelope, right? And we remember, hopefully, that the dew pressure curve is the lower curve, and then the higher curve up here is the bubble pressure curve, changing with the mole fraction of the more volatile component. Okay, and specifically in this case with our flash drum, we are between these two curves, right? We have to be somewhere between those curves at some specific pressure and then, of course, a constant temperature. And what that means is that our mixture will be separated into vapor and liquid phases. What we're interested in doing is finding the amount of our feed that is in the vapor phase, the amount that's in the liquid phase, and the composition of each phase, of course. So there is actually a third quantity for the mole fraction of the more volatile component that I'm going to add here, and we're going to call that Z1. And that is simply the total mole fraction of our more volatile component in our feed at the start, right? So if we have some total feed coming in that's 10 moles per second, we could say, and I'll draw a little dashed line, that the mole fraction of benzene, our more volatile component, Z1, is 0.4. Okay? And that is obviously very important for us, but once it gets inside this flash drum at that set temperature and pressure, we are going to have a separation with vapor on the top and liquid on the bottom for our mixture, which means for our mixture, we're going to have X1, we're going to have a mole fraction of benzene that's in the liquid phase, and then Y1, we're going to have a mole fraction of benzene that's in the vapor phase. Let's start writing some equations. We have our feed coming into the flash drum, and then we understand that this flash drum is part of a separation process. So it's a stage in which it's separating the vapor phase and the liquid phase to separate the components in our binary mixture. So we know that the flow rate going in, our feed, T, is going to be equal to the sum of the flow rate of vapor exiting from the top and the flow rate of the liquid exiting from the bottom. In the next video, we're going to be dealing with a binary mixture of benzene and toluene again. So what we can do here is perform a mass balance with the more volatile component. As I said before, we can use Z1 to represent the mole fraction of benzene, in this case, in our feed that is flowing into our flash drum. What that means for us is that the total moles of benzene that we have in our feed can be represented by T, the flow rate going into our flash drum, multiplied by the mole fraction of benzene in our feed, Z1. We can do the same thing with the vapor phase and the liquid phase, right? We know that the moles in the vapor phase multiplied by the mole fraction of benzene in the liquid phase, Y1, is equal to the moles of benzene in the vapor phase, and then we can do the same with the liquid phase. So this would be L times X1. I'll remove the dots there. So now we have two equations. The next thing I want to talk about here, of course, is Raoult's law once again. We can assume Raoult's law is valid here because we have an ideal mixture of two hydrocarbons. So let's write that. So what is Raoult's law? That is going to be the mole fraction of some component in the liquid phase multiplied by its pure saturation vapor pressure. And that is equal to the partial pressure, which is the mole fraction of that component in the vapor phase multiplied by the total pressure, of course. Okay, so how might we use this to end up deriving the Rachford-Rice equation? There's one quick manipulation I would like to add here that will help us when we're trying to derive the Rachford-Rice equation. And that is, we can represent the ratio of the mole fraction of some component in the vapor phase to the mole fraction in its liquid phase by Ki. So we can say that Ki is equal to the mole fraction of that component I in the vapor phase divided by its mole fraction in the liquid phase. So you can think of that almost as a certain partition coefficient between the vapor and liquid phase for a certain component in the mixture. Not exactly, but it's sort of like that. Now, there is also one other thing we can see with this, right? Looking at Raoult's law, so if I divide both sides by xi, and then I solve for this Ki that would be on my right-hand side of the equation, so I would divide both sides by the pressure. So this is equal to the pure saturation vapor pressure divided by the total pressure. Now, why is that important for us? Well, we need to remember that we are doing the simplest case, right? We know the temperature and pressure that we'll use in the next video of our flash drum. So that's super important. What this means is we can use the temperature to find the pure saturation vapor pressure of each component, and we already know the pressure, our denominator, which means that we can find this Ki value for both the benzene and the toluene. So that will be extremely helpful for us when we are trying to solve for 4 different unknowns. So let me specify those up here real quick. Obviously, we want to know the total amount of moles in the vapor phase, right? So we want to know V, and we want to know L. We want to know the moles in the liquid phase, of course. And obviously, that would actually be represented as moles per second, a flow rate that's exiting, from below for the liquid phase or from the top for the vapor phase. So we want to know those. But we want to know the composition of the vapor phase and the liquid phase to see what separation we're getting. And really, this just means that we want to know Xi and we want to know Yi. And again, we can find it for the more volatile component, and then obviously we can use that to find it for the less volatile component because we're just dealing with a binary mixture, right? So if I have 80% benzene in my vapor phase, then I know that I have 20% toluene in that vapor phase as well for a binary mixture. Deriving the Rachford-Rice equation starts with a very obvious observation, and that is that the sum of the mole fractions in the vapor phase subtracted from the sum of the mole fractions in the liquid phase is equal to 0. Let's think about this real quick. If we had 40% benzene and 60% toluene in our vapor phase, let's see, that would mean 40% toluene in our liquid phase and 60% benzene in our liquid phase as well. If we subtract these, right, and remember these are fractions, these are mole fractions, then this is like saying that 1 minus 1 is equal to 0. So I think this is actually really cool. And what we can do, actually, to make things a little easier on ourselves is just represent this as one sum and then have a difference inside of this sum. So we'll call this yi minus xi. And then remember that for our sum, we could have n number of components in our mixture. It doesn't have to be like the binary mixture we're going to use in the next video. So really, this could be n number of components in our mixture, and obviously the more volatile component is always the lowest number, and the lowest number that we would start with would be 1. So we'll do I equals 1 at the bottom there. Now, let's think about what sort of substitutions we can make. I see one right off the bat, and that is with Ki. So to get everything in terms of Xi would be quite nice. It's the mole fraction in our liquid phase. We have to remember that Yi and Xi, the mole fractions in the vapor phase or the liquid phase, we do not know those. And in fact, that's really what we're trying to find. So we have to remember that we need to do substitutions to get rid of those. So we see here, and hopefully I'm not too far down, I'm not, that Ki times Xi equals Yi. Okay, so we can write that down here. I'm going to ignore the sum for now. Okay, we can put it back at the end. But we have this, right? Okay. Now, what here do we not know? Of course, we don't know the mole fraction in the liquid phase. So now we need to do some more manipulating to figure out a substitution that we can make. Let's take a look at the second equation that we had before, which had a mass balance for the more volatile component. And actually, I want to factor out xi over here. That way we just see it once. So this would be xi times ki minus 1. Okay, and this is the second equation that I'm talking about. So we can do the ki times xi equals yi substitution again. So we would have t times zi equals v ki xi plus l xi. And remember that L, actually this is V and L are definitely unknowns, right? That's the moles in the vapor phase that is flowing out at some rate from the top of our flash drum, and then the moles per second in the liquid phase that's exiting from the bottom of our flash drum. And then obviously we're trying to actually get an expression for xi that we can substitute into there. Okay, so that's the goal of this manipulation. So to decrease the amount of unknowns, we can use equation 1 here. So we can substitute in for L the difference between our feed and the moles that's exiting in the vapor phase, right? So that would be T minus V, okay? And as we just did up there, we can factor out xi, of course. So we factor out xi to get this. And then we divide both sides to solve for xi. And then we can also factor out v here as well. So we get v times ki minus 1 plus t. And oh shoot, that's in the denominator. My bad. Sorry about that. So you would have this on top. Getting lazy with my subscripts as well. But anyway, that's what this would look like. Now, what do we want to do here? Well, this is where things get a little bit interesting. I think this is super clever. Basically, we have the moles that are exiting, that flow rate that's exiting from the top in the vapor phase. What we can do here that I just think is so clever is we can basically divide the top and the bottom here by our feed rate, right? And let's just take a look at what that gives us. So for xi, we would get zi, and then we would have v over t, right? Ki minus 1 plus 1. Okay? So what might this be? Let's talk about this expression that we have for xi. So this is our expression for the mole fraction of some component in the liquid phase for our mixture. And what we see is that when we make this substitution, I erased everything so that this would become clear. We make that substitution so that we have the final Rachford-Rice equation. And that is going to be represented by this sum, right? So in the numerator here, we would have zi times xi minus 1 quantity. And then there was nothing in the denominator up here. So we would just have this again. And this is absolutely fantastic. Because with this substitution of the mole fraction in the liquid phase for some component, we definitely don't know that. So with that extra substitution, we have finally narrowed it down to just one unknown in this sum here. And in the next video, we are going to code some stuff in Python, of course, and we're going to find this value v. This is our only unknown, and that is the flow rate in the vapor phase that is exiting from the top of our flash drum. So that's this v that we're trying to find. We can then use equation 1 to find the flow rate in the liquid phase that's exiting from the bottom of our flash drum. And then using equation 2 here, we can find the composition of the vapor phase and the liquid phase to examine the quality of our separation. And this is going to be pretty simple because for us, this N up here is actually going to be 2, right? We're just going to have benzene and toluene. So once we find the mole fraction of, let's say, benzene and toluene, we can obviously see that they add up to 1. But what I should have said, actually, is we'll find the mole fraction of benzene in the vapor phase and the mole fraction of benzene in the liquid phase. You can also find the mole fraction of toluene in the vapor phase and the liquid phase by doing, obviously, 1 minus y1 equals y2, right? So that's extremely cool, I think. I think that's extremely useful, and as you can see, especially from past videos, the manipulation we had to do, all the algebra, to figure out the Rachford-Rice equation really isn't that difficult. It honestly reminds me of what we did when we were trying to find an equation for the due pressure. We basically make a very obvious observation. We describe that reality with some sort of equation. And in this case, again, it was a summation. But if you remember what we did for the due pressure equation, we basically said that when the first drop of liquid is formed when we're trying to find the due pressure, we basically just said that the sum of the mole fractions of each component in the liquid phase has to equal 1, which is so obvious, similar to how obvious this expression is that we ended up using to derive this for the Rachford-Rice equation. So I am very excited to get right on it and jump into our next video in which we'll be using this expression, coding some stuff up in Python to actually find our 4 unknowns given a temperature and pressure for our flash drum. So thank you so much for watching.